Hello and happy Thursday. I trust that you will all be super productive since I can't be there. We'll do a typical video lesson / get your own work done. Make sure you're ready for this upcoming unit, which is about piecewise functions, which sounds scary, but it's really not. In fact, there won't be really anything new at all this unit, just a chance to review lots of stuff we've been doing already this semester. So first things first, make sure you keep in mind the following announcements. Check Google Classroom. If you didn't read them thoroughly, there's information about the quiz, which is tomorrow, and a reminder that there's a homework check coming up next Wednesday, followed by a group quiz next Wednesday. And then there will be a test Friday, and the test Friday will be on both the logs unit and the piecewise unit, which we're starting now, which is very brief. So just a couple of days on piecewise functions, and then that will be the whole exam next Friday. All right, so you were to have completed on your own or in your teams, or on your own and then in your teams, this first page, and so here is a chance for you to check your answers. If you haven't done it yet, stop the video. You need to be able to do this first page without assistance. This is all about logarithms. So here, go ahead and pause the video if you need to, check your answers. And if you are satisfied that everything matches up, then it's time for us to move on. If you have any questions about what you're seeing here, check with your group mates. Okay, make sure that you're careful about the f of 0 prompt there. That is undefined. You cannot input 0 into this function. The function doesn't exist there at 0. All right, so let's get into piecewise functions, and keep this function in mind here, the log base 3 of x minus 4, because we're going to use that in just a moment. So if you flip to this next page, we'll do an example here together of how we think about piecewise functions. And this one we've already looked at here, this logarithm. We already saw that this was the log base 3 of x minus 4. So that one we're just going to play with again. But what you can see here is that on our graph, at first glance, it looks like we might be talking about 3 different functions. And you'd be right in thinking that this has 3 different functions, except that we're going to call this entire thing one function. This whole thing is going to be p of x, and p of x is going to contain 3 pieces of separate kinds of functions. So we call this a piecewise function. Piecewise function. And that's kind of a weird name. I apologize. But it's a piecewise function because it contains pieces of several functions. And those can be all different functions, those can be the same functions. They'll all have some sort of equation or rule, but each piece may have a different rule. So we call this a piecewise function. So again, the most important takeaway of these 30 seconds is that this here, what you're seeing, is actually one entire function represented with 3 pieces. And you'll notice here, if we were going to try and draw this function, if we were going to trace it with our pen, I can get a fancier pen because that's how I roll. If we were going to try and trace this function with a highlighter here, I would trace this parabola, and then I'd have to hop up. I'd have to lift my pen to trace the next piece. And then I'd have to lift my pen again to trace the third piece. And what that means is that because my pen is sort of jumping all around, we call this function either, you can call it discrete or you can call it discontinuous. Right? So it's discrete or discontinuous. And the reason for that is that it is disconnected. Oh, I think I spelled that wrong. There. So it's disconnected. If the function were all connected, if you could draw it from end to end without ever lifting your pen, you would call that continuous. But in this one, we're looking at one that is discrete or discontinuous. So then let's kind of get into the details here. One of the things that's going to be the most complex with piecewise functions is that you're going to need to pull together equations for each of the pieces. So it's important that you kind of scan the piecewise function and decide what it is that we're looking at. So here, this piece here, this is a parabola, so this will be quadratic. This is a straight line. It is linear. Since it's a horizontal line, it's a linear, but it's also a constant. Constant means it's not changing. This is consistently at -7. And of course, this one over here is a logarithm. So our three pieces are a quadratic, a parabola, a linear constant, and a logarithm. And let's go back and review. And so some of you are going, oh man, I have to write equations for quadratics. I can't possibly remember how to do that. This will all come back to you. You may need to do some Googling. You may need to do some reviewing in AM support. But a quadratic here, so if we're going to write the piece of the parabola, we have to find our vertex. And it looks to be here at -10 and -9. Which means it's shifted left 10, so we'll have x plus 10, so that's a left shift of 10, and shifted down 9, and since it's quadratic, it'll be squared. Now the question, is there any stretch? Well, to the right 1 and up 2, to the right 1 and up 1, 2, 3, 4, 5, 6, to the right 1 and up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's that 1, 3, 5 pattern, but doubled to 2, 6, 10. That implies a stretch of 2. Since it opens upward, it's a positive 2. Now, if you're kind of shaking your head thinking, oh, I don't remember any of that, guess what? Time to practice. Thinking about the domain here is going to be a tricky piece of piecewise functions, but you'll pick it up quickly enough because it's not any different than thinking about a domain of just one function. So if we're looking at the quadratic and we're thinking of domain, remember domain is sort of thinking about vertical lines on the horizontal axis. So you can see that the left end of our domain is here at -12. And the right end of our domain appears to be here at -7, excuse me. So then the question of what kind of symbols is about looking at the endpoints, included or not included. Those are filled in, those are closed. Both of those are closed, which means both of those endpoints are included. The linear function, the constant, if we want to write this equation, any linear function will sort of have just a very straightforward y equals, and then what does the y equal? Here it equals -7. Right, so y equals -7, or in this case, since we're pulling together a piecewise function, we can just write -7. And the domain, well, what are the left and right boundaries? So here's a left boundary, here's the right boundary. Left boundary appears to be -5. Right boundary appears to be 2. Examine the circles. On the left, I see an empty circle, open circle. On the right side, I see a closed circle, which means on the left, it will not include 5, and on the right, it will include 2. We've already written the equation for the logarithm. Yay, that's done. So just think for a moment. We call this a piecewise function. Why do we call it a piecewise function? Well, it's pretty simple because the equation is defined in pieces. And if we want to write all of p of x, right? So before we wrote one equation here, we wrote one equation here, and then we have a third up here. It's kind of a mess. But if we want to define p, just p, if we want to just write what p of x is, because p of x is made up of those three pieces, well, then we define p of x equals, and we use this ellipses to say that, hey, we're about to define p of x in several different ways. And we say it's defined by this quadratic for this domain, and then it's defined as this constant, this linear constant, on this part of its domain. And then finally, it's defined as a logarithm for this part of its domain. So you can see the domain is kind of a bunch of bits and pieces. The domain starts at -12. The domain extends out to infinity. But then there are some gaps. this piece goes up till -7, but this piece doesn't start again until -5. So there's a gap. This piece ends at 2, and the next piece doesn't begin again until 4. So again, there's another gap. And you can actually see that if you look. There is a gap in the domain here where the graphs, where you have to hop from one graph to the other. Those are gaps in the domain. And again, that's why we called this discontinuous. Another word for that is discrete. Disconnected is how it looks. That's not actually a very mathy term. So we won't use that when we talk about it, but that may be what you're thinking. Evaluating and solving is the last piece that you'll need to be able to consider. And the only real new thing about evaluating and solving is that you always have to keep in mind which piece of the function. So if you're evaluating p of 31, for example, you have to consider who's in charge of 31. Is it the quadratic piece? Is it the linear constant piece? Is it the log piece? Where's the input of 31? So check the domain. Where does 31 lie? Does it lie between -12 and -7? No. Does 31 lie between -5 and 2? No. Is 31 bigger than 4? Yes. So 31 is contained in the domain between 4 and 31. So to evaluate p of 31, you'll use the log piece. And newsflash, you already did this one on the first page. Right, so 31 minus 4, and then you concluded that that all equaled 7. How about p of 0? For an input of 0. Well, again, where does 0 lie? Does 0 lie in between 4 and infinity? No, because 0 is less than 4. Does 0 lie between -5 and +2? Yes, it does. And in fact, you can see on the graph, if you draw your eyes up the graph, here's an input of 0. You can see that the correct output would be here on this linear function. All right, so we'll take a look here. P of 0 will equal -7 because the linear function is in charge of that. All right, so evaluating means think about which piece. You'll have to make a choice to choose the appropriate piece. Sometimes you'll be able to see it on the graph, other times you'll plug it in. And so then the last piece to think about is solving. And actually, we've been doing this kind of solving forever. Where does p of x equal -1? Well, that could be all over the place. Look at the graph. That's your best method for evaluating in piecewise functions. If you don't have a graph, you will have to set each of your pieces equal to -1 and solve. But for today, let's just look at the graph. Here's where y equals -1. Here's where y equals -1, and you can see that that actually is represented by 3 different locations on our piecewise function. It intersects twice with the parabola at what appears to be -12 and -8. Let me double check that. I would hate to get something wrong on a video and then have you all laugh at me. -8, -12. Yes. Okay, -12 and -8. And then we saw as well that it equals -1 right there. And the logarithmic piece, oh hey, did we already solve that one? I believe we did. Right, so also 3 and a fourth. 3 and a fourth. All right, there's your basic introduction to piecewise functions. This is about a 12-minute video. Feel free to watch it again. It'll stay up on the Google Classroom. What I want you to do now is, with your group or on your own, take a look at this second option, right? This second practice problem. You can see it's a piecewise function, and I want you to do this on your own. I want you to construct equations for each of the pieces, and then think about the domains, and then end it by writing a single piecewise function for this. Now, I repeat, I am not posting the solutions to this one. You will need to figure it out and turn it in. If you get totally stuck, you can check video 2. Video 2 will have a few hints for you, but I will not be posting the solutions. You will need to get the correct answers on your own and turn this in. Remember, this is your proof of work